Hello everyone, my name is Nick Baldwin, and today I will be presenting Unrocking Drones, Foundations of Acoustic Injection Attacks and Recovery thereof. Before we begin, I would like to acknowledge the original authors of the paper listed here. Originally, this paper was presented at the Network and Distributed System Security Symposium in 2023, and a link to the paper itself is listed here on the page if you'd like to check that out for yourself. So before discussing the details of acoustic injection attacks discussed in the paper, I'd like to go over some relevant background first. So the primary target that was studied for acoustic injection attacks was just common commercial drones, which are often equipped with a variety of sensors such as gyroscopes, accelerometers, barometers, global navigation satellite systems, and even optical flow sensors. When combined, they all form a package, which is an essential part of the governing control loop known as the attitude and heading reference system, which is a really important part of computing the attitude, which is your roll, pitch, yaw, and position, forward, back, up, down, left, right of the drone. So all 6 axes of motion. So to minimize errors, the values of those sensors are typically combined in a complementary sense, which is referred to as sensor fusion. Notably, the extended Kalman filter is a popular sensor fusion algorithm. However, since sensors are used to measure physical properties and physical phenomenon, as we'll find in this paper, they can consequently be influenced by malicious signals transmitted from adversaries. So even though drones are equipped with a variety of sensors, an attacker that is interested in compromising a drone with an acoustic signal is going to be most interested in the details of a MEMS IMU, which stands for a Microelectrical Mechanical System Inertial Measurement Unit. So put plainly, those typically consist of a gyroscope and an accelerometer on a single integrated chip, which is an important feature for things like lightweight drones that wouldn't be able to lift a traditional IMU in many applications. So you can see the difference in size between the Apollo 11 IMU and a modern MEMS IMU. However, this miniaturization of those features from a large mechanical system to a microelectrical mechanical system is what makes them vulnerable to acoustic injection attacks in particular. So to understand why an acoustic attack might be effective against a MEMS IMU, I think it's important to discuss the underlying physics principles of what might be happening within that particular sensor package. So while an IMU typically consists of both gyroscopes and accelerometers, I'm going to briefly discuss accelerometers because ultimately they use similar physics principles, and if you can visualize an accelerometer, you can visualize a gyroscope. So in particular, accelerometers, per the name, are going to be interested in measuring acceleration of linear motion, and that's done by measuring the inertial force that's induced within the sensor itself. So normally these are designed to measure the X, Y, and Z accelerations separately. And the way that's done is within the sensor, you have a small proof mass on a spring that proportionally deflects according to the experienced acceleration. So in particular, this is going to be related to Newton's second law and Hooke's law, which are going to be representative of acceleration and spring displacement in particular. So as you accelerate, that mass is going to move and deflect within the sensor package in such a way that's linear according to Hooke's law, and that linear deflection can then be read as a change in capacitance and a change in output voltage from the sensor. So once you have a variable sensor output voltage that's related to a physical phenomenon, then you can use that output voltage to be read by a controller and ultimately interpreted to an acceleration signal. However, the downside of a system like this is that it's a sprung mass, and in particular, sprung mass systems are vulnerable to resonance in particular. So an acoustic attack is going to be most interested in finding the resonant frequency of the accelerometer or gyroscope and then trying to induce a signal exactly at that resonant frequency. So zooming out a little bit from the IMU sensor itself, we can now cover what an acoustic injection attack is seeking to do. So on the figure on the right, you can see that we have an acoustic injection signal, which is going to be broadcast at the resonant frequency of the MEMS structure itself. And the resonant frequency is the frequency that's going to vibrate that object with the highest amplitude. So that's matched to the particular geometry and physical properties of the construction of that sensor. So if you can do that and inject a signal into the structure, that is going to induce that electrical output signal through the amplifier, analog filter, and analog digital converter, and that compromised signal ultimately leaves the sensor package and finds its way directly input into the flight controller, which is going to consist of that AHRS loop. So if you can influence the signal from that sensor, which is going to be directly what's influencing the control of the drone rotor output, you can ultimately cause that to crash. So if a drone is trying to maintain a consistent acceleration, heading, orientation, or even just flying in a stable position, if you can trick that flight controller into thinking that it needs to compromise and adjust for an erratic acceleration that it's experiencing, you can ultimately cause that drone to make a poor decision and crash. Ultimately, what adversaries are trying to do is exploit that particular vulnerability. It's easier if you have identified the exact hardware that you're trying to influence, because then you would know what the actual frequency that you're trying to drive at would be. However, even if you don't know the exact MEMS IMU that's being used within the drone, you can still attempt to inject an acoustic signal over a range of different frequencies and observe the output. So you can effectively do a scanning sweep to try to find the resonant frequency of that MEMS structure. So with all that covered, we can finally get into the overview and overall findings of the research paper. So the researchers set off with two different objectives as part of their problem statement. The first being they wanted to make drones accomplish their planned missions under acoustic injection attacks. And then they also wanted to be able to recover the benign sensor values from a compromised signal. To do that, the researchers needed to create a simulation testbed for simulating an acoustic injection attack on a MEMS IMU. So they were able to use that to directly resonate a MEMS IMU, which they then gathered sample data from and were able to use in various software in the loop, sometimes abbreviated SITL, and hardware in the loop simulations, which would be HITL simulations. So from that, they were able to log the position and status of the drone, with and without attacks. And ultimately, they were able to create a sensory recovery technique using a denoising autoencoder, which they dubbed the unrocker. To define their solution, the researchers first had to define an adversary threat model. So they assumed that they would have a pretty advanced attacker that could remotely transmit a strong acoustic and an ultrasonic signal to initiate a denial of service or spoofing attack. Additionally, they assumed that their adversary would possess comprehensive knowledge of the structure and operating logic of the target, which would mean that with knowledge of that drone, they would be aware of the onboard sensors and ultimately the resonant frequencies, but then also there's the sampling frequencies of the drone's controller. Additionally, they assumed that the acoustic attack would be performed on all MEMS sensors simultaneously, which is important because if you were to attack everything simultaneously, that would incapacitate any common mitigation strategies that would involve supplementary or redundant sensors. And lastly, they assumed that the attack could continue for a prolonged period of time. So putting all of that together, you have an adversary threat that is capable of discovering the resonant frequency, broadcasting that resonant frequency continuously on the drone until the desired outcome is achieved, which would in this case be crashing the drone. So after defining the threat model, the researchers were then able to start testing and designing their solution. So ideally, you'd be able to do that with a physical test bed, but the researchers deemed that that would be prohibitively costly for a variety of reasons. In particular, it would require a high-quality speaker and a physical drone. The speaker would then have to be aimed at the flying drone target and emit a precise signal for the duration. And if you were to do that successfully, would ultimately be destructive to the drone. So if you're trying to do multiple iterations, that was deemed to be pretty costly. So instead, the researchers chose to develop a software-based acoustic injection testbed based off the PX4 simulator, which is a popular open source drone project. And in particular, that simulator also enables SITL, which stands for Software in the Loop, and HITL, Hardware in the Loop simulations. So briefly, an SITL is an entirely software-based simulation that's used for testing the flight controller software of drones, whereas the hardware-based simulation actually utilizes the physical hardware and physical board, which is helpful if you're trying to model or simulate the potentially hardware-related issues such as operational or scheduling times, which is actually important to the rest of the findings from the researchers as it would end up. So utilizing their software-based simulation testbed, the researchers were able to do a variety of software and hardware-based situation testing. So to do that, they specifically chose a 3DR solo drone and would wait for it to hover at a stable altitude of approximately 2.5 meters for 15 seconds before they would inject the malicious signal. So interestingly, although it's widely accepted that IMU sensors will cause the drone to crash if they're resonated, the researchers actually found that the drones did not crash in a majority of the software-based experiments. However, they would crash in every hardware-based simulation. So to further prove this out, the researchers did specific testing on both gyroscopes and accelerometers separately. So effectively what they would do is they would induce a sine wave, representing the acoustic signal, and they would vary that the amplitude and frequency of that signal to test the overall results. So the figure for the gyroscopes in particular was with a signal at 4 radians per second and 100 hertz. And as you can see in the software-based simulation, you had a very, very minor change in altitude from the acoustic signal. However, in the hardware-based simulation, you can see that it made the drone rapidly change height, heading, and orientation, and ultimately crash the drone. Similarly, they did a similar tests for accelerometers, where they resonated the amplitude between 0 and 90 meters per second with an induced frequency between 5,000 and 5,250 hertz. And like the testing on the gyroscopes, the software-based simulations had little to no effect on the drone's position, but with the hardware-based simulations, caused an incredibly erratic flight path and ultimately would crash the drone. So the important questions from that initial testing was, why would the drones not crash in the software in the loop experiments, and what ultimately causes that inconsistency between the software and hardware-based experiments? So after some additional experiments, the researchers determined that it was actually the robust control logic that was preventing the drone crashes in the software-based experiments, and they attributed that to 2 different factors. First, the sensor drivers contain digital low-pass filters, or LPFs, that ultimately filter out unwanted signals, such as the resonant frequency that is going to be at a really high frequency. And in addition to that, the in-band frequency of the control logic was considerably smaller than that of even the low-pass filter boundary. So with those two factors combined, the resonant frequency was not really being sampled in this software-based simulation, which would explain why the simulation really did not have any real impact on the drone's heading and orientation. So what exactly are digital low-pass filters, and how are they able to prevent the drone from crashing in the software simulations? So a digital low-pass filter is often employed in control systems to eliminate unwanted band signals from the control logic. So this doesn't necessarily pertain directly to acoustic injection attacks. You would employ one just to potentially eliminate noise or even the harmonic components from rotation of the rotors in particular in drones, and you would want to be able to eliminate that from the signal. So digital low-pass filters in particular are located in the software drivers of the drones that retrieve the sensor values. And in the particular experiments that the researchers did, the drone often employed a digital LPF with a cutoff frequency of 30 Hertz. Which notably is considerably lower than that of an acoustic resonant frequency. To test the in-band frequency range of the control logic employed in the drones, the researchers performed an SITL test with the disabled low-pass filter, and the results showed that the drones would crash from projected frequencies between 0 and 5 Hertz. For signals between 5 and 125 Hertz, which is the max that they tested in this scenario, the drone was able to fly successfully. So what this actually demonstrates is that the drone's control logic works on a frequency between 0 and 5 Hertz, and therefore most of the resonant signal would be completely ineffective at modifying the actual control range of the drone itself. So putting all of this together, the drones did not crash due to the digital LPF and narrow in-band control range. If the MEMS IMU resonant frequency is not within the control range, then the drone shouldn't crash. So this ultimately ends up posing the question of what actually causes the drones to crash in the hardware-based experiments. And what the researchers found was that sampling jitter is actually the critical factor for drone crashes in the hardware simulations. So what they discovered was that the resonant sensor signals are actually being dispersed in the hardware simulations, which would not be dispersed in the software simulations. So if you take, for example, a resonant frequency of 5,100 Hertz, the induced frequency will be approximately 100 Hertz with the 250 Hertz sampling frequency of the drone. So effectively, the resonant frequency is incredibly undersampled, which is what causes that induced frequency to be so much lower. So looking at the figure on the right, we have multiple different plots. The blue plot is showing the benign signal. So effectively, we're looking at a frequency of 0. So you have a drone at rest. However, the green plot is showing the spectrum of an ideal resonant frequency in a software-based simulation. So you can see that it's peaking around that 100 Hertz induced frequency. The orange plot is showing the resonant sensor signal before the low-pass filter is applied in the hardware-based simulation. So you can see that it's also grouped around 100 Hertz, but there's significantly more spread and noise in the signal. And the red plot is what's ultimately conveyed to the control logic. So that is that same orange plot after the low-pass filter has been applied. And what you can see is that that dispersed signal in the hardware-based simulation is actually partially getting through the low-pass filter cutoff of 30 Hertz. You can also note that the unfiltered in-band noises are extending through that 0 to 5 Hertz control range logic. So what you have here is in the hardware-based simulation that just that dispersed noise in the data effectively is actually able to get past all of the protections in place and ultimately influence the acceleration and rotation readings of the drone. So after getting these results, the researchers sought to determine the driver for the differences between those hardware and software simulations. Ultimately, they determined the root cause to be due to sampling jitter, which is an inconsistent timing delay in retrieving the actual sensor values due to things like small drifts in clock signals, crosstalk, etc. And so this has the effect of spreading and dispersing that ideal frequency across a wider band of sampled frequencies. So the higher the jitter, the wider the dispersion. Notably, the resonant frequency, which is going to be generally above several thousand hertz, is significantly undersampled on these drones in particular, where they only have a sampling frequency of 250 hertz. And unfortunately, undersampled signals are even more susceptible to sampling jitter, which in this case is going to magnify the effect of an acoustic injection attack. In the figure at the bottom right, researchers plotted the actual sample time versus the ideal sample time of 4 milliseconds, or in this case, in the figure, 4,000 microseconds. Their findings showed that the jitter within the software simulation was essentially zero, while the hardware and real drone readings were actually significantly higher at 457 microseconds and 103 microseconds respectively. To prove out this theory even further, the researchers duplicated the previous hardware-in-the-loop experiments onto a physical Pixhawk board, which is a popular flight controller, while injecting actual sound with a speaker. And the results confirm the earlier findings where the sampled resonance is dispersed across a wide band and the residuals are ultimately retained in spite of the low-pass filter. So the previous experiments showed that the sampling jitter caused the residual acoustic signal to impact the control band of the drone. However, the researchers wanted to prove that jitter was the root cause of drone crashes under acoustic attack. So they attempted to emulate the results without sampling jitter on an actual 3DR solo drone. They recorded and inserted resonance software sensor models into the drone's firmware, but they slightly modified the timestamps so that the resonance signals were exactly aligned with the drone's sampling frequency of 250 Hz. In this way, they were able to plot the effect of the drone's position under acoustic attack with and without sampling jitter. As seen on the top two figures on the right, the drone's position was barely impacted when the accelerometers and gyroscopes were resonated when the resonance signal was aligned with the drone's sampling frequency. But the same cannot be said about the drone's position in the bottom two figures, which show an erratic flight path before ultimately crashing. So these experiments were able to demonstrate that 1, acoustic attacks are in fact effective against commercial drones, and 2, that sampling jitter is the root cause for why this style of attack is effective. Moving on to mitigation, here are 3 commonly accepted mitigation strategies. The first being the addition of low-pass filters, which through the course of this experiment were actually found to be ineffective due to the sampling jitter that spreads the undersampled acoustic attack signal against the in-band control frequency range. The second commonly proposed strategy is the addition of sampling randomization, which is the modification of that sampling frequency rate. And previous studies have found that this can be an effective strategy against spoofing attacks and MEMS sensors, but this study found that it would actually increase vulnerability to denial of service attacks. And this is due to the increased probability that you would be sampling the undersampled resonant sensor signal similar to jitter. And it's also important to note that ideal uniform sampling is fundamentally infeasible on real hardware, as covered previously, which then ultimately leaves the last potential mitigation strategy, which is the benign sensor signal recovery. So if the idea that sampling jitter spreads that acoustic resonant frequency across the control band and has a similar appearance to noise in that control band, are there potential strategies for a denoising technique? And ultimately this becomes the basis of the unrocker solution presented in this experiment. The mitigation strategy that the researchers developed and tested was dubbed the unrocker, which was designed to recover the benign sensor values from the compromised signal. To make this system work, they needed a robust denoising algorithm that would be able to successfully prevent drone crashes. Popular heuristic filters such as the Savitsky-Golay and Wiener filters were tested, but were ultimately unsuccessful at preventing drone crashes on the simulation testbed. So instead, the researchers chose to develop a deep neural network-based solution called a DAE, or denoising autoencoder. So after training this model, Unrocker is designed to operate in between the sensor drivers and the flight controller. So the way this works is the Unrocker receives the sensor data from the sensor drivers. The received data is stored in a queue and transferred to the pre-trained DAE model, and then after denoising, the data is then transferred on to the controller. The researchers tested the Unrocker for a variety of different signal strengths and different scenarios. The error reduction figures are included in the table on the left, but in summary, Unrocker is able to successfully recover the benign values from a compromised signal. The results are provided in a more visual format in the figures on the right, where the red represents the compromised signal, green represents the recovered signal after Unrocker processing, and the blue represents the reference or benign signal. As you can see, the recovered signal is nearly identical to the benign signal in most cases. It is important to note that Unrocker is a proof of concept that shows promising results, but does not effectively operate in critical real-time scenarios. Recall that the ultimate goal is to make drones continue to fly to planned destinations by recovering the benign sensor readings in real time. However, the PX4 sensors are updated every 4 milliseconds, and the machine learning-based approach requires several seconds of processing time. The researchers believe that this limitation of processing overhead was beyond the scope of the paper and could be addressed in future studies, though. So, to wrap everything up, I'd like to give a brief summary of everything presented thus far. First, MEMS IMU sensors are indeed vulnerable to acoustic injection attacks due to the inherent limitations of their geometry and mechanism of operation. Second, techniques such as utilizing low-pass filters or sample randomization are not robust defense measures against acoustic injection attacks. Third, sampling jitter was found to be the critical root cause of drone crashes when subjected to acoustic attacks. And lastly, Unrocker's machine learning approach was able to demonstrate better denoising performance than other heuristic approaches. Unrocker was able to successfully recover sensor data to an extent that would prevent drone crashes, but additional work is necessary to adapt to real-time scenarios. And that concludes this presentation to Unrocking Drones, Foundations of Acoustic Injection Attacks and Recovery thereof. Thank you for listening, and I look forward to answering any questions you have on the discussion board.